Welcome back to the deep dive. Today, we're going to be diving into the world of machine learning security,
Okay.
specifically a type of attack called data poisoning.
Interesting.
We're going to be unpacking a research paper titled Wild Patterns Reloaded, a survey of machine learning security against training data poisoning.
Okay.
And given your expertise in mathematics, machine learning, and data science,
Right.
I think you'll find this deep dive particularly insightful.
Yeah, I think this is a really critical area, especially as,
Yeah.
machine learning models are being integrated into more and more real-world systems.
Absolutely. And this paper starts by painting a rather unsettling picture.
Uh-oh.
Imagine a world where seemingly harmless data can be subtly tweaked to make a machine learning model misbehave
Oh, wow.
in very specific ways.
Okay.
That's the essence of data poisoning.
Right.
And the paper emphasizes that this isn't just a theoretical threat.
Yeah, absolutely. The paper cites a survey by Kumar et al.
Hmm.
From 2020 and a more recent one by Grosse et al. In 2023, highlighting that data poisoning is a top concern for industries deploying these ML models.
And they back this up with some real-world examples that really drive the point home.
Yeah, one prominent example is Microsoft's chatbot Tay,
Right?
which was designed to learn language through user interactions.
Yeah.
But unfortunately, malicious users exploited this and flooded Tay with offensive language, effectively poisoning its training data.
Wow.
And this isn't limited to English language chatbots. Similar incidents have occurred with chatbots in other languages, including Chinese and Korean.
It's a stark reminder that these systems are vulnerable to manipulation, even in seemingly innocuous ways.
Yeah.
The paper also mentions how search engine autocomplete features, which many of us rely on every single day,
Right.
can be manipulated to spread misinformation.
Absolutely. Attackers can poison the autocomplete suggestions by strategically injecting biased or misleading queries, influencing what users see, and potentially shaping their perceptions.
And then there's the chilling example of Google's image search being targeted.
Yes. The paper describes how a group of extremists attempted to poison Google's image search by submitting mislabeled images of portable ovens with wheels tagging them as Jewish baby strollers.
Oh my goodness.
This disturbing incident highlights the potential for data poisoning to be used for malicious propaganda and hate speech.
These real-world examples certainly paint a sobering picture of the threats we're facing.
Yeah.
So let's delve into the technical details.
Okay.
The paper categorizes data poisoning attacks into three main types:
Okay.
indiscriminate, targeted, and backdoor.
Okay.
Can you walk us through those?
Of course, indiscriminate poisoning aims to degrade the overall performance of the model, reducing its accuracy on any input. A common technique here is label flipping,
Okay.
where the attacker manipulates the labels of training data.
So instead of learning the correct associations, the model learns incorrect relationships, making it less accurate across the board.
Exactly. Now, targeted attacks are more subtle and insidious. They aim to cause misclassifications for specific target samples while maintaining the overall model accuracy.
The paper gives the example of a stop sign being misclassified as a speed limit fine due to a targeted attack.
Right.
This type of attack is particularly dangerous because it can be harder to detect.
Indeed. And then we have backdoor poisoning,
Okay.
which is like creating a secret trap door in the model. The model functions normally for most inputs, but when presented with a specific trigger, it misbehaves in a predetermined way.
So, for example, a backdoored street sign detector might function correctly in most cases, but when it encounters a stop sign with a specific, seemingly innocuous sticker on it,
Right.
it misclassifies it as a speed limit sign.
Precisely. The attacker essentially embeds a hidden trigger into the model during training.
Now, to carry out these attacks, the attacker would need some level of access or knowledge about the target model and its training data, right?
Yes, the paper discusses different scenarios in a white box attack.
Yeah.
The attacker has full knowledge of the training data, the model architecture, and even the test data.
Wow.
This gives them a significant advantage in crafting effective attacks.
That sounds like a worst-case scenario, but likely not the most common.
You're right, in many real-world situations, the attacker might have limited knowledge, what we call a black box attack.
Right.
They might rely on techniques like creating a surrogate model to approximate the target model and then transfer the attack.
Fascinating. The paper also provides a framework for categorizing attacks based on how the attacker can influence the learning process.
Yeah.
Can you elaborate on that?
Certainly, they look at scenarios where the attacker can influence the initial training from scratch,
Okay.
fine-tune an existing model,
Mm-hmm.
or even subtly control the model training process itself.
Wow.
They also categorize attacks based on the type of data perturbation,
You're right.
like label flipping, where labels are changed, and clean label attacks where the data itself is subtly modified without changing the label.
So it's a multidimensional classification system that considers both the attacker's capabilities and their approach to manipulating the data or the learning process.
Exactly. This framework provides a comprehensive view of the attack landscape, helping us better understand the different ways attackers can exploit vulnerabilities in machine learning models.
So now that we've sort of covered the types of attacks and the attacker capabilities, let's shift gears and explore the defenses.
Okay.
How can we protect these machine learning models from data poisoning?
So the paper does a deep dive into 6 main defense strategies.
Okay.
Training data sanitization, robust training model, inspection model sanitization, trigger reconstruction, and test data sanitization.
Okay, let's break those down one by one.
Okay.
What's the idea behind training data sanitization?
As the name suggests, it's all about cleaning up the training data before the model even sees it.
Okay.
The goal is to identify and remove any poison samples that could mislead the model during training.
So it's like weeding out the bad apples before you make the pie.
Exactly. Techniques like outlier detection come in handy here.
Yeah.
We can analyze the data and look for data points that significantly deviate from the norm, which could be a sign of poisoning. Another technique is spectral signature analysis,
Right.
which examines patterns in the data to identify anomalies that might indicate poisoning.
Interesting. So it's not just about removing obvious outliers, but also about detecting subtle patterns that might reveal malicious intent. What about robust training?
Yeah.
How does that work?
Robust training is about making the model itself less susceptible to the effects of data poisoning. Instead of just focusing on the data, we try to modify the training algorithm to be less sensitive to outliers or noisy data.
So we're trying to build a model that's strong enough to withstand some degree of contamination in the training data.
Precisely, techniques like robust optimization are used here,
Okay.
where we adjust the training process to minimize the impact of potential outliers on the model's parameters. Another powerful technique is differential privacy, which adds noise to the data during training to protect individual data points from being identified and targeted by attackers.
It's like adding a layer of camouflage to the data, making it harder for attackers to pinpoint specific targets for manipulation. Okay, what about model inspection?
Yeah.
How do we inspect a model for signs of poisoning?
Model inspection is like detective work.
Yeah.
We analyze the trained model to look for any suspicious behavior or anomalies that might indicate poisoning. One technique is activation clustering,
Okay.
where we examine how different neurons in the model activate in response to different inputs. Unusual patterns in these activations could reveal the presence of a backdoor.
So we're not just looking at the model's outputs, but also peering into its internal workings to see if anything fishy is going on.
Yes, and another method is neuron inspection, where we delve deeper into individual neurons to understand their role in the model's decision-making process.
Okay.
If a neuron seems to be overly sensitive to a specific trigger, it could be a sign of a backdoor.
Fascinating stuff. So let's say we've detected a backdoor through model inspection. What can we do about it? That's where model sanitization comes in, right?
Exactly. Model sanitization is about cleaning up a compromised model.
Okay.
This might involve retraining the model on a clean data set, hoping to overwrite the backdoor.
So it's like giving the model a second chance to learn from uncontaminated data.
Yes, we can also use techniques like fine-tuning, where we adjust the model's parameters slightly using clean data to try and nudge it away from the backdoor behavior. And there are more specialized techniques like pruning.
Pruning?
Yeah.
Is that like trimming a tree?
It's a good analogy.
Wow.
In pruning, we remove unnecessary connections in the neural network, hoping to eliminate the backdoor along the way. Another approach is data augmentation, where we generate additional training data from the clean data we have, effectively diluting the influence of the poison data.
So model sanitization is a toolbox of techniques aimed at rehabilitating a compromised model. But what if we want to be more proactive and try to identify the backdoor trigger itself? That's where trigger reconstruction comes into play, right?
You got it. Trigger reconstruction focuses on identifying the specific trigger that activates the backdoor. This can be incredibly valuable because if we know the trigger, we can potentially neutralize it.
So it's like finding the secret password that unlocks the backdoor's malicious functionality.
Precisely. There are several approaches to trigger reconstruction.
Okay.
One is reverse engineering, where we try to trace back the model's decision-making process to figure out what input pattern is triggering the backdoor behavior.
Right.
Another approach is pattern analysis, where we look for recurring patterns in the data that are consistently associated with the backdoor activation.
It sounds like a mix of detective work and code breaking. Okay, and finally we have test data sanitization.
Right.
How is that different from the other defenses?
Test data sanitization is unique because it happens at test time, not during training. The idea is to sanitize any potentially malicious input at the point of inference to prevent the backdoor from being activated, even if it exists within the model.
So even if we haven't been able to detect or remove the backdoor during training, we can still try to block it at the last moment.
Exactly. Techniques here might include pre-processing the input data to remove potential triggers, using anomaly detection methods to flag suspicious inputs, or employing ensemble methods where we combine the predictions of multiple models to reduce the risk of relying on a single, potentially compromised model.
It's like having a multi-layered security system with checks and balances at each stage to minimize the risk of a successful attack.
That's a good way to think about it. Each of these 6 defense strategies has its strengths and weaknesses, and they often work best in combination with each other.
So it's not about picking one best defense, but about building a comprehensive defense strategy that layers different techniques to provide robust protection.
Precisely, it's about understanding the threat landscape, assessing the specific risks, and tailoring a defense strategy that's appropriate for the situation.
This deep dive into the world of defenses has been fascinating, but as we've seen, data poisoning is a constantly evolving threat, and attackers are always looking for new ways to exploit vulnerabilities.
That's right. It's an ongoing arms race. The paper delves into the historical development of data poisoning attacks, tracing their evolution from early heuristic-based methods to more sophisticated, mathematically grounded techniques.
Oh, wow.
Would you like to explore that aspect?
Absolutely. Understanding the historical context is crucial for appreciating the current state of the field and anticipating future challenges. So let's delve into this history of data poisoning.
Okay.
Where did it all begin?
So the roots of data poisoning can be traced back to cybersecurity research.
Okay.
Early work in the mid-2000s demonstrated how attackers could manipulate training data to compromise machine learning models,
Right.
used in security applications like spam filters and intrusion detection systems.
So the idea of poisoning data to mislead machine learning models isn't entirely new.
Right.
What were some of the early approaches to data poisoning?
So initially, attacks were often based on heuristics and application-specific techniques.
Okay.
There wasn't a unified mathematical framework to describe or analyze them.
So it was more about finding clever ways to exploit vulnerabilities in specific systems.
Yes, but a pivotal shift occurred in 2012.
Okay.
When Zhao et al. Formalized indiscriminate poisoning as a bi-level optimization problem.
Bi-level optimization, that sounds complex.
It involves solving 2 optimization problems simultaneously.
Okay.
In the context of data poisoning, the attacker seeks to find the optimal way to perturb the training data to maximize the model's error, while the model itself is trying to minimize its error during training.
It's like a game of chess where both players are making moves at the same time trying to outmaneuver each other.
That's a great analogy. This bi-level optimization framework really changed the game for data poisoning research.
Yeah.
It allowed for the development of more systematic and targeted attack strategies.
So instead of just randomly flipping labels, attackers could now precisely calculate which data points to poison and how to perturb them to achieve specific goals.
Exactly. And this led to the emergence of targeted poisoning attacks,
Right.
where the attacker aims to misclassify specific target samples while maintaining the overall accuracy of the model.
Making them harder to detect.
Right.
The paper mentions the work of Ko and Liang in 2017, who demonstrated how to poison a model to misclassify a particular image. And then Shafahi et al. In 2018 and Gaiping et al. In 2021 refined this approach with their work on feature collision.
Right, feature collision involved crafting poison samples that mimic the features of specific target samples, inducing misclassifications for those targets.
It's amazing how these attack techniques have become increasingly sophisticated over time, but as attackers have become more advanced, so have the defenses.
Yeah.
The paper also traces the evolution of defenses against data poisoning.
Right.
Can you walk us through that history?
Of course, early efforts focused on relatively simple techniques like removing outliers from the training data, which we now call training data sanitization.
So it's like reading out the bad apples from the training set. But as attacks became more sophisticated, Defenders had to develop more robust methods.
Exactly. That led to the development of robust training methods,
Right.
like robust optimization and differential privacy, which we discussed earlier. These methods aim to make the models themselves less susceptible to data poisoning.
Instead of just cleaning the data, you're trying to make the models more resilient to manipulation.
Right. And around 2018, we saw the emergence of model inspection techniques
Yeah.
to analyze trained models for signs of backdoors or other anomalies.
Like the detective work we talked about earlier.
Yes, researchers developed methods like activation clustering to analyze patterns of neuron activations and identify potential backdoors. And if a backdoor was detected, then model sanitization techniques like retraining, fine-tuning, pruning, and data augmentation were employed to try and clean up the compromised model.
So it's a constant back and forth attackers developing new techniques and defenders coming up with countermeasures.
Exactly. And in 2019, we saw the emergence of trigger reconstruction techniques to identify the specific triggers that activate backdoors.
Like the neural cleanse technique proposed by Wang et al.,
Right.
which aimed to reverse engineer the backdoor trigger. Fascinating stuff.
Yeah.
This historical overview really highlights the coevolution of data poisoning attacks and defenses. It's clear that this is an area of active research with ongoing challenges.
Yeah.
What are some of the key research directions that the paper highlights for the future of data poisoning and its defenses?
So one important direction is the development of more realistic threat models.
Okay.
Many current evaluations of data poisoning attacks make assumptions that are quite favorable to the attacker,
Okay.
such as assuming the attacker has complete knowledge of the model or can poison a large portion of the training data.
So the evaluations need to be more grounded in real-world constraints where attackers might have limited knowledge or resources?
Precisely. Another key direction is designing more efficient and scalable data poisoning attacks.
Right.
The bi-level optimization framework, while powerful, can be computationally expensive.
Especially for large models and data sets.
Yes. So research is exploring ways to make these attacks more efficient, perhaps by leveraging techniques from hyperparameter optimization or meta-learning to speed up the optimization process.
Interesting. And on the defense side, what are some of the key areas of focus?
So we need to continue developing defenses that are more robust, generic, and scalable, capable of protecting against a wider range of attacks, including those that adapt to known defenses.
Thinking outside the box.
Exactly. And of course, we need to continue developing rigorous evaluation methodologies to ensure that defenses are truly effective against a wide range of attacks, including those that adapt to known defenses.
So it's a continuous process of innovation and refinement, both on the attack side and the defense side.
Absolutely. It's an ongoing arms race, but the research community is actively engaged in this challenge, and I'm optimistic that we'll continue to develop techniques to make machine learning more secure against data poisoning.
This deep dive has been incredibly insightful. We've covered a lot of ground from the different types of data poisoning attacks and their real-world implications to the evolution of defenses and the challenges that lie ahead. Any final thoughts for our listener before we wrap up?
As we've seen, securing machine learning against data poisoning is a multifaceted challenge. It demands a deep understanding of both attack techniques and defense mechanisms. But the good news is that we have a vibrant research community actively working to make machine learning more secure, and there are many promising research directions being explored.
It's an exciting time to be involved in this field for our listener. I encourage you to continue exploring this area, delve deeper into the research, and consider contributing your own expertise to this crucial effort. This deep dive has given us a lot to think about and highlights the importance of staying informed about the latest developments in machine learning security. Thank you for joining us, and we'll see you next time on The Deep Dive.